when we look at the ideal gas law, one thing you might notice as we write out PV equals nRT, there's nothing in this law that depends on the identity of the gas particle. So there's not a mass or anything like that, or we don't have to have a different gas law for nitrogen versus hydrogen versus argon. The ideal gas law works for all these gases. So there must be some sort of theoretical underpinning to this ideal behavior, right? So works for all gases when we're under ideal conditions, I'll say, must be some theoretical underpinning. And that's what we're going to be talking about in this chapter, is the kinetic theory of gases. And this is a theory that makes some basic assumptions about how gases behave, and then uses those assumptions as a model to figure out some of the fundamental properties of the gases. And the kinetic theory of gases is really useful because we can derive lots of interesting information that can be useful when you're considering gas phase reactions or gas phase processes where you need to know some of these properties. You can get a good estimate from this model. So things that we can derive are, you can get back to the ideal gas law and show that if you make these assumptions, you get ideal gas behavior. We can find out things about speeds of particles. How fast are they moving around? We can look at velocity and speed distributions. And for these speeds, I'll say average speeds. Velocity and speed distributions. So, if you have a sample of gas, what fraction of the gas is moving at a certain velocity or speed? And finally, we can look at collisions, or collision frequency specifically we can derive from this. How often do gas particles strike each other, hit each other? That last one is particularly important when we're thinking about gas phase chemical reactions, because for a reaction to happen, things have to come in contact with each other. And in the liquid phase, things are constantly in contact with each other, but in the gas phase, that's not necessarily true. And so how often do things hit each other can tell you how fast you might expect reactions to occur. So this is awesome information that we can get from this. And like I said, we have some assumptions that underlie this kinetic theory of gases. So what are those underlying assumptions? We have three main ones, and many of these are similar to the assumptions that I talked about with the ideal gas law. So one, the gases, or I should say the gas particles, so either atoms or molecules, are in ceaseless motion, right? They just keep buzzing around. Random motion, and follow Newton's laws. So we could think of them as small billiard balls bouncing around. Two, the gas particles behave like hard spheres. This is the billiard ball part. So we're going to ignore the fact that many molecules are not spherically shaped, of course. But we're just going to assume that they are. And to a first approximation, this works pretty well. Hard spheres and only interact through collisions. So we assume they have no electrostatic interactions, right? So they have no dipole moments, no induced dipole moments. We're ignoring all those effects, and only interact through elastic collisions. All right, what do we mean by elastic collisions? So an elastic collision is a collision where no kinetic energy is lost. Basically, nothing absorbs any energy. So nothing squishy, everything's hard, and they just bounce off each other. So going back to the idea of like a billiard ball, right? They don't deform when they hit each other, they just knock against each other. And so just to reiterate, we are assuming no dipoles, no induced dipole or dispersion, forces happening between molecules. All right, so that's one of the assumptions that we're making. And then our final assumption that goes into the kinetic molecular theory, number 3, is similar to what we've already said about the ideal gas law, that the size of the gas particles is negligible. Compared to the average distance traveled between collisions. Another way of saying this mathematically is that the volume of our particle, whether it's an atom or a molecule, is approximately equal to 0. We're just making that assumption. Okay, and with these 3 assumptions, we can then start looking at the physics as what happens if you have these assumptions. So in the next video, we'll actually look at some simulations of what this behavior looks like.